So we have binomial distributions. We actually worked with binomial distribution already. You guys did some binomial expansion for me. Remember we had the quantity something raised to the 8th power. We used Pascal's triangle. We figured it all out, the n choose r and all that kind of stuff. And it was pretty quick and painless to work through. What this is a little bit different offshoot from it. What we're able to do here with the binomial distribution is that we're going to look at the idea of probability of an event. We're going to find the probability of some event that it's going to occur. We're going to call that a success rate. If it occurs, it's successful. If it doesn't occur, it's a failure. So you have success, fail. The other thing that we look at for binomial distribution is that when we are looking at a large sample, and this is kind of where they get into with like pharmaceuticals and stuff, when they're starting doing testing about effectiveness on certain stuff. What is the probability of somebody having an adverse reaction out of a sample test group? That's the kind of stuff that we're looking at here. So if we take a large trial of things, and out of that large trial, we're going to sample 6. And we're trying to see, of those 6, do 2 of these things happen? What's the probability of 2 things happening out of 6 out of a giant population? And you're able to whittle things down a little bit more by using this binomial distribution. The way I'm going to work this through is I'm going to try and mirror an example they give us in the book to set up everything. So that way you can refer back and forth to it. Now, the other thing that's really nice about binomial distribution is that there is a really long-winded formula to solve all of that, but there's a button. Yay. And being able to utilize the button to make this stuff work is really key to understanding which one to choose from. Okay? So when we're talking about a binomial experiment, don't write this out here. I want you guys to think that there are going to be some sort of n independent trials. We're going to try to do something a certain amount of times. Really, really easy example. I want to flip a coin 50 times. Each time I flip a coin, it's independent of each other trial. The first flip has no bearing upon the second, has no bearing upon the third, and so on. Kind of make sense on that? What I'm going to ask then is, out of that 50 flips, what is the probability that I'm going to get tails exactly 6 times? Yes, ma'am. I'm explaining what all this says. It's the probability that I can find up to 20 of them being tails. What's the probability that I can have at most 20? The probability have at least 30 of them. There are all of these little probabilities that we can find by using what's called a binomial experiment, because you're looking at a success failure. The probabilities that we're going to be given, well, you're going to have to be given some probability. You'll notice that if you have a probability, a p-value of, I don't know, 0.3, if that's a probability of success, what's the probability of failure? 0.7. It is its complement. All right? So the probability that it would not occur would be 1 minus it. We use complements a lot in this section because it's easier to count with. So the easiest thing to do is the following. A generic experiment. Oops. No, not really. We're close. Sorry if I can get this to fit. Put your heads on the desk and cover your eyes. I will ask you a question. No.
It's going to be on the test.
Is this going to be on the test? Yes!
Yay. Got the question?
No. So I'm going to ask you a question. No peeking. No reason. I didn't ask you a question yet.
Yeah, I have a question.
What the heck?
I'm definitely going to see
That would be real.
Now we know for the feet.
There's no peeking.
Wow.
Unaware of, but we heard him peeking at
Doesn't mean you had to lift your head up. How do you know I was going to go get you guys
We
pizza?
could have died.
I could have got you pizza, but now I'm
The
not.
school could have burned that. What's the question?
You,
now?
there's no
I don't know. I haven't gotten there yet.
Oh,
You guys peeked.
Hey, validate it first.
No, actually, I did.
I did.
Damn!
Yes,
They were
Sam
too
said I
involved.
did.
Anyway, here's your question.
Oh. Wait, we're supposed to put our heads together.
Yes, put your heads down. I'm going to ask you a question. Really?
Got the question?
I didn't ask a question yet. So, I'm going to ask those of you that believe that UFOs exist to raise your hand.
Fine UFO.
Do you
Yeah, the
extraterrestrial unidentified flying object? Okay. Now, I want you to raise your hand if you believe that the extraterrestrial unidentified flying objects do not exist. No! Well, I have an issue right now because there's 24 of you and only 19 have voted. So let's try this again. Raise your hand if you believe that UFOs exist. Raise them all the way up in the air with your heads down. Don't exist. Okay, one of you still hasn't voted.
I'll vote for him.
It's probably Brandon.
Guys, this is come on. Yes, raise your hand. Okay. Now we have the total. Thank you. Now you may lift your heads up. I don't know. And then maybe somebody just raised their hand, just raise their hand because they're annoyed. So basically what's happening here is that we have success and failure. We have a total of 24 people in the classroom. And of our class, 14 of you say yes. And 10 out of the 24 of you say no. So what I'm looking at is this value that I'm going to call P. P is going to be my probability of success, my success rate, if you will. So my success rate here is be 14 out of 24, 7/12, which is some number I don't know off the top of my head, but I'm going to use some decimal. Thanks.
0.58. Just remember this.
So if my success rate is 0.58, my failure rate is
0.42.
So what this is basically telling me is that we have 24 trials in. And I'm looking, in our group, we have n equals 24. That's for the number of trials. I'm going to ask, of the 24 trials we have in the room, I'm looking for a successful sampling of, let's say, 3 people. I'm going to look for 3. I'm picking 3 people out of the group. I'm going to pick the 3 to have the success value of P, 0.58. And what we're doing here is a binomial distribution. I am picking 3 out of a certain amount of trials to have, what is the probability that 3 of you people that I randomly select believe in UFOs? Knowing that out of the 24, 58% of the people believe in UFOs. What is the probability that I'm going to pick 3 that do? this is a binomial experiment. This looks really gnarly. I don't believe I just used the word gnarly, but it looks really weird when you look at the generic formula. Let's see if I can find it real quick. We'll go back to this. Here it is.
Oh, no, those are yours.
So we have success, where it is n choose k, p to the k, 1 minus p to the n minus k. These are all buttons on a calculator. We had a total of 24 trials. We're picking 3 for success rate of 0.58 to the third power times 1 minus the 0.58, which is our failure, to the n minus k, in this case 24 minus 3. The idea here is that we have to keep track of number of trials, number that you're picking out of the trials, and your success rate. As long as you keep those straight, it's just pressing the button. Now, when we do this, it's over here. We go to our calculator. What was our C? Our C was math, probability, 3. We start typing in values. 24, C3. And now I can just type in 0.58 to the third times parentheses 1 minus 0.58 to the. Can I figure out 24 minus 3 in my head? I can. If you don't trust yourself, could you write that as your exponent, 24 minus 3?
That's what I did. Just to be safe.
You can do it. And I get this.
No, you can quit.
Okay?
Sam, what did you do wrong?
And it just means that there's the probability of picking exactly 3 that have that. It's. Did I throw an extra value?
That's what I said.
Oh, that's just times. Okay. So that's what you're looking at as far as success and stuff goes through. Now, the reason that this is such a small probability is because we're picking out of 24. Now, if I lower that down and just want to sample size out smaller, let's say I want to take a sample of 6 and hope that 3 of the 6 people have it. Yes, sir.
Wait, is that 4%?
No, it's 0.0. If you move this over, it'd be like 0.0000004.
Oh.
Okay, so it's a small percent. That
So 4% plus 14 over 24 times 40.
No, why don't we test it
because you're looking, because what you're looking at there, this is when we're looking at a modeling idea. We're modeling it via what do you call it? The binomial here. If it was going to be 14 out of this, 14 out of this, you're just assuming that it's just no matter what, everybody is going to be that same percentage. You have to weight it against a sample. So when you go back to looking at what this would show, let me get rid of this. When we're looking at the probability of exact success, and it worded a little bit differently, I might not have said it as well as I had hoped. Let me read it to you verbatim here. Where's the? Oh, did I exit out? Oh no, I didn't. Here it is. When you read it verbatim, it tends to make a little bit more sense. And I was trying to mirror the idea in what they did in the book. Let's see here. So you can see how this works.
Oh, so it's probably that exactly 3 people?
Yes.
So it's not just if you choose 3 people.
Right. It's the exact part, and that's where it comes in. You want only 3 people to believe in UFOs out of the 24, knowing that 58% of people believe in it.
So it's not at least 3.
And that's going to be worded differently. And that's where it's going to come into.
So you're taking samples of your area?
Correct.
Okay, that makes a lot more sense.
And that's where this comes down to. Now, what's kind of cool about this stuff is that I try to do this with what they had in the book so you can kind of follow through back at it. to be honest with you, you guys in third hour both believe in UFOs a lot more than apparently the rest of the world does. But then again, this book was from, I don't know, a long time ago in a galaxy far, far away. So if you supposedly you randomly survey 6 adults, what is the probability that exactly 2 of them believed in UFOs? What we did here is we randomly selected 24 people, and we wanted exactly 3 people to believe in UFOs. That's why it seemed to be so much smaller, because you have a larger sample size, taking exactly 3 to occur. If we do this with a 6, if we're just picking 6, and you want exactly 2 people to believe in UFOs out of a sample size of 6, you're doing the same basic idea. Your N value is 6, K value is 2, and P, in this case, would be 0.37. So as you follow through that via the book itself, or the way that it's written out, you'd have a 6, choose 2, 0.37 to the K, which is 2, and then it's 1 minus 0.37 to the 6 minus 2. Now when you throw that in the calculator, you're going to get a more workable number because you have a smaller sample size that you're starting with. Let me show you this little trick then, what happens. So if I do this one, so it's 6, choose 2, 0.37 squared, parentheses, 1 minus 0.37 to the 4th. A better workable probability. So if you have a smaller sample size, you're looking for fewer success, you start to see that it becomes a little more feasible, if you will. Here's a nice little trick, though. Your calculator has a binomial distribution function already built into it. So you don't have to worry about using this C value, P value to a power, 1 minus P to some other power. There's a binomial distribution, and there's 2 forms of it. And it comes into play when you want exactly a certain amount, or when we talk about at least or at most. So there's going to be 2 different versions of this. On your calculator, if you hit second vars, vars is next to Pergam and clear. Pergam and clear. Then you will see that there are 2 options. We have Bino PDF and Bino CDF. And I will show you the difference between the 2. Poisson. Poisson. These distributions are all statistical distributions. Poisson distribution is a stats thing. Geometric, this is also a statistical thing, distribution set. Here we're talking about binomial. It's either going to be PDF or CDF. Binomial PDF we're going to use when we want exact K value. When it says K equals 3, K equals 4, something like that. We're going to use the CDF version for when it's at least, at most, fewer than, more than, because it does something different, and I'll show you what it does here in a second. We use that for at least or at most K. So now it's a matter of what buttons do you press. Now some of you guys have one operating system, some of you guys have another. What I want you to do is hit Bino PDF first. And it's telling you, some of your screens is showing up with trials and all that other stuff on there.
Base.
Where did I post it? I will show you what it all means in 1 second. So as you go through your values here, when you hit Bino PDF, remember second bars and then it's A. If you have a calculator showing up like this, you're starting out with your trials. Your trials stand for N. The example we just did had 6 for your trial, so you put a 6 in. We wanted exactly how many people to believe in UFOs out of those 6? 2. That's our X values 2. Our P value was the percentage, was 0.37, and our X value was 2. I don't know what paste means. Copy paste. Now it's spitting up that. For those of you guys that did not have that option to put in, what you're going to put in when you opened up, it opened up a parentheses for you. First thing you put in is the number of trials, comma. So you put a 6. You didn't hit second bars. So if yours is showing, we're just open up a parenthesis with Bino PDF, parenthesis open. First thing you put in is your number of trials. In this case, it's going to be a 6. After that, do you know where the comma button is? It's between the 7 and the sign. Then you put in your P value, 0.37. And then you put in your comma. How many do you want exactly? 2. And then you hit enter, and lo and behold, they're the same number. Thanks, Shimkey. Fine. Everybody but Shimkey gets to use this.
Okay.
Shimkey, you have to do the long way.
Wait, okay.
Yes.
Do the first one again, like the first version that you did.
Yeah. So second vars. Binom PDF. Number of trials. How many? We had 6 trials. P value was 0.37. The number exactly you want for your K value is 2. It spits it out, and there you go.
All right.
Okay? So when you're trying to find a value that is exact, that's what you put. That's what you press. Yeah.
Is this possible to do by hand?
Yeah. I don't want to raise point. I don't want to do 0.3. Don't do that. You're going to break my calculators. I don't want to do 0.37 squared. I don't want to do 0.63 to the 4th. I mean, you can, but the old way of doing this was to do an L1, L2 in your lists, and then do a histogram and do a zoom 9 and do a calculate version. Hey, there's a button. Let's use it. It's quicker. Okay. So let me show you what the difference between the exact versus the at least at most. Here's the other one. When we look at the same data set, and I'm just going to show you what this looks like here. And I want to talk about getting, what is the probability that at most 2 of the people would believe, out of your 6 trials, would believe in UFOs? Well, the word at most means you could have, would it be equal to 2 and greater, or equal to 2 and less? Equal and less. So that means that out of the 6 people, we could have nobody, 1 buddy, 2 buddies. So we're looking at these values here. Old form, what you would have to do is calculate those 3 separate probabilities, which, as you can see, is pretty easy, and add them all together. Well, what the Bino CDF does, it accumulates and it counts them for you. So C is for when you're counting multiple binomial distributions. What it will do is that it will count, when you do a Bino CDF, it counts up to whatever you give it as a k value. It'll count up to k, so it starts at 0, so it'll do the bino PDF of 0 plus the bino PDF of 1 plus the bino PDF of 2. It'll do that calculation for you and add up the 3 separate possibilities.
If you want to do at least 2.
Then you do the complement. If I want to do at least 2, that means I'd want 2, 3, 4, 5, and 6. Now, it'll only count up to whatever you tell it to. So if I do 1 minus up to this, it's going to account for all the rest of it. And that's how it works. I'm glad you asked that. That's how that stuff works. So by putting in the CDF, when you do that, same spot, second, vars, and this one's option B. It's still asking the same things. Trials, it's going to ask you your p-value, it's going to ask you your x value, or in this case, remember x stands for k. And it's going to accumulate after count 0, 1 to whatever your k value is. It counts up to k. So we had 6 trials. P-value was 0.37, and I want to count up to 2. Same deal for what you're putting in your parentheses. Number of trials, whatever your p-value is, and what you're counting up to. Yeah?
So you said the complement is 1 minus 2?
Yes.
So it'd be 1 minus 2?
No. It'd be 1 minus the bino PDF, bino CDF. I'll show you it again. So this is at least 2. I'll show you. It takes a second to understand the difference for the at least, at most.
So you find the bino CDF with the p-value and then subtract what you get?
You can do one of 2 ways. When I'm doing, this one was an at least. This was an at most. At most means you want 2 and fewer. If I want to do at least, I want 2 and greater, which means I'm going to count below the 2 and subtract it from 1. And I have an example for that here in a second. So as I was saying, when I do one like that, so slow. When I look at this, my k value is less than or equal to 3. That means it's going to be at most 3. I'm going to switch it. I'm going to say I want to be, greater than or equal to 3, which means I want k to be at least 3. I want at least 3 successes from out of the 14 with a p-value of 45. That's what that looks like. So I get 3 successes out of this. Now remember, what the bino CDF does, and CDF is when you're looking at greater than or less than problems. The CDF is going to start at 0, the CDF is going to count from wherever you tell it to, and it's going to go to 0. It's going to go 0 up to that number. I'm looking for all of these. Do I include the 3? No. I want below the 3. I want to count these guys. If I count these guys as happening, the complement would be that happening. So what I would do is 1 minus the bino CDF. Our n value for trials is 14. My p value is 0.45. And my k value would be 2. It means the same thing. The calculator uses x, the book uses k. So what I'm doing here is instead of, remember, because you could sit there all day long and add up bino PDF of 3 plus bino PDF of 4, bino PDF of 5, and so on and so forth, all the way up to 14. Well, that's a big pain in the butt. Nobody wants to do that. Take the smaller chunk and do the complement. It's just a quicker way of doing it. Okay? It's a much, much faster way. Yes, ma'am. What do you mean?
It doesn't go past 14, it has to be 7.
Correct. Yes, there is a set specific number of trials that you have, and going from there. Yeah.
Why is that the last value in the
Because remember what the Bino CDF button does, it counts up to whatever that value is.
You did 0, 1,
And 2, because I want to be at least 3. So I have to include 3 and go up. So if I did a 3 here, which means I'm forgetting to count 3 with the rest of the stuff. So I pick the value below it.
So, oh, you just picked the value below.
Yeah, the next value below.
Right.
That's all it is. And that's how you work with the CDFs. So a PDF is for when you have an exact value. A CDF is when you have to count a bunch of the values. You're looking at at least, at most. Yes, ma'am.
The final, will it ever be graded?
Should be, because you're looking at a probability. The probability is always between 0 and 1. I'm looking at what is the probability out of these 14 trials, I'm going to have at least 3 successes. So I can have 3 successes, 4, 5, 6, 7, and so on. The probability that I can have that many successes, if I know that the probability of success is 45%. So I'm looking at what's the probability that I'm going to have at least this many work, and so on. And that's how you were talking earlier, like why isn't it just multiplying straight through? Because you have all this other stuff going on.
I'm going to complement 1 minus, but it can't be graded.
Yes, sir.
K and N are never going to be fractions, right? They're always whole numbers.
Yeah, because you can't have half the trial.
I figured it's double check.
Yeah, these would be integer values. Yeah, I mean, they might give you a p-value as a fraction, but yeah, I mean, we're talking fractions, like, oh, it's a half. Oh.
They got 9/10 of the way through in the trials. They didn't finish it.
So then what you'll be able to do here today is that we're going to look at the probability of randomly guessing the given number of correct answers on a 30-question multiple choice test. So what's the probability of randomly selecting the right answer on one question? 25% if you have 4 chances. So what's the probability out of 30 questions then? I'm going to get exactly 2 right. What's the probability I'm going to get exactly 30 of them right? So that's the idea of what we're doing. Now, you could also write this as what's the probability I can get at least 30 of them, at least 20 of them, and so on. But these are what you're able to do with binomial distribution style problems. Okay? Now, the other thing is that works out with this is that as your number of trials start to grow larger and larger and larger, the way that these histograms, which we don't really worry about so much, they start to do is they start to norm themselves out. And this is where the bell curve, I forgot what it's called. This is where the bell curve comes from. This is where we start to talk about mean and standard deviations, the confidence in the mean. So those of you guys who start to take ACTs and stuff like that, you probably start to see standard deviations of that. That's where all this stuff is heading. And we'll finish this stuff tomorrow with the word problems, and then we'll start bell curve on Friday. I want you guys to do this with pages. This is 742. I'd like you to go 10 through 34 evens.
What page is it?
742. Do not worry about drawing histograms. I'm not going to make you do that. What did I say, 34?
Yeah.
Okay. Probability is fun.
What's the probability?
Good chance you're joking.
I'll do that.
Shimke, why aren't you doing your homework?
I don't have paper.
I have paper in the back. Shimke, help yourself. Shimke, you're fun to harass.
Yeah, I know. That's because I'm easy to harass.
For